Hey guys, in this video we are going to see about spectroscopy, its basics and some insights on rotational, vibrational and electronic spectroscopy. So we have a light source and a matter. The study of the interaction between light and matter is called spectroscopy. We know about the spectrum of light, that is the visible spectrum. It consists of violet, indigo, blue, green, yellow, orange and red as shown here. These together compose the white light. As we move from left to right, wavelength increases and energy decreases as they are inversely proportional. This visible spectrum is actually a part of what is called the electromagnetic spectrum as shown. It consists of radio waves, microwaves, infrared, visible, ultraviolet, X-rays and gamma rays. As we move from the right to left, wavelength increases and energy decreases. These individual radiations are called the electromagnetic radiations, abbreviated as EMR. It is called electromagnetic radiation as it has both electrical and magnetic components. It is represented here. There are two waves perpendicular each other. One is in the plane of the screen and the other perpendicular to the screen. In order to view the second wave, let us rotate the image in the x-axis. A more precise view can be obtained by rotating the wave in the z-axis. Here, if the one painted as yellow is the electric component, then the other is the magnetic component. Let us paint it as blue for better visibility. The distance between two peaks here is the wavelength. A technique which uses radio waves is called NMR, which stands for nuclear magnetic resonance. A technique which uses microwaves is called the rotational spectroscopy. The technique which uses IR radiation is called the vibrational spectroscopy. A technique which uses UV and visible light is called the electronic spectroscopy. A technique which uses X-rays is called XPS, which stands for X-ray photoelectron spectroscopy. A technique which uses gamma rays is called the Moss-Boyer spectroscopy. First, let us see the rotational spectroscopy. In order for a molecule to be microwave active, it should have a permanent dipole moment. Let us consider the example of HCl. Here the small red ball is the hydrogen and the large blue ball is the chlorine. Since chlorine is more electronegative than hydrogen, the chlorine pulls the electron density towards itself and hence the bond is polarized and a dipole moment is not zero. The dipole moment is a vector quantity and has both direction and magnitude, which is represented below the image. When we have the molecules in the absence of microwaves, the molecule is not rotating. When it is exposed to microwaves, it rotates rapidly as there is an increase in rotational energy. That is, there is the rotational transition from lower rotational energy level to higher rotational energy level that is happening. Now let's move on to rotational spectroscopy. A molecule is said to be IR active if it has a change in dipole moment during vibration. Let us consider the example of CO2. Here the small black ball is the carbon atom and the large red balls are the oxygen atoms. Since oxygen is more electronegative than carbon, the oxygen pulls the electron density towards itself and hence the bond is polarized. But since the dipole moment is a vector quantity, both the dipole moments cancel off, resulting in a net dipole moment of zero. But during vibration, asymmetric stretching to be specific, there is a change in dipole moment, making it IR active. In the absence of IR radiation, the molecule would be vibrating. In that aspect, even at absolute zero Kelvin, the molecule is expected to be vibrating. When the molecule is exposed to IR radiation, the vibration amplitude of the molecule increases and there is no change in vibration frequency. Moving on to the final topic, the electronic spectroscopy. When a molecule contains pi or non-bonding electrons, it is expected to be active in the UV and visible region. This is because the UV and visible radiation have enough energy to cause electronic transition. Let us consider the scenario where the red ball represents the electron and the blue plates represent the molecular orbitals. The highest occupied molecular orbital is called the HOMO and the lowest unoccupied molecular orbital is called the LUMO. When the sample is exposed to UV visible radiation of particular wavelength, which is selected by the slit, electronic transition takes place from the HOMO to the LUMO. In the near future, the other techniques will be explained. Thanks for watching.